But there won't be a review session next week just because Thanksgiving's the next day and I'm going home. So none of that, but it will have one before the next exam on whatever day that is, the 29th, when we get back. What that means is that just make sure you're keeping up with chemistry a little bit over the break. Like you don't have to look at it while you're on doing any Thanksgiving plans if you have any, but like maybe that Sunday, just like kind of refresh your brain, because you will have an exam the week you come back. And it is 5 days, so you do have time to like prepare for it. But you don't want to like completely lose everything in the meantime. With that being said, this is the last in-class exam you have to take, and then your final is the week after if you're in the 1240 or like that Tuesday, if you're in the 3 o'clock. But yeah, are there any questions for me before we do today? No? Okay. Anything specific we want to see today just from what we've done so far? Go ahead. Yeah. Okay. Okay. And did he say he's giving you a practice final exam? No, just the old practice exams? Okay. Yeah. So I can put together some review questions for y'all for the final, just that's kind of like cumulative over the year, over the semester, as an additional review source. Yeah, and I'll work on that in the meantime. I'll probably post that after exam 7. Anything else? Okay, anything else about or anything specific about the stuff we've covered so far in class? Getting N as in like number of electrons? Yeah, absolutely. Alrighty, so we started redox reactions. And so the main thing to remember with redox reactions is that this is 2 things happening simultaneously. Right, this is 2 things happening simultaneously. We have reduction, which is where the RED comes from. And what does it mean to be reduced? We're gaining what? We're getting reduced. Are we getting more negative or more positive? We're getting more negative. So this is going to gain electrons. We also have oxidation, which is where the OX come from. And what happens when we get oxidized? We're losing electrons. Okay, so the big thing to remember here is that in a redox reaction, you have something that's always getting reduced and something that's always getting oxidized, right? They're going to be equal and opposite with these things that are happening simultaneously. Okay. Absolutely. So you can have a reduction reaction in where something is getting reduced or it's gaining electrons, or you can have an oxidation reaction where something is getting oxidized or you are losing electrons. You can also have a oxidation reagent, I believe is the other word he uses it. That's right. Yeah, oxidation reagent, or an oxidant. This will be the thing that gets reduced in your redox reaction. Okay. You can also have a reduction reagent or a reductant. And what do you think a reductant does or is? It's the thing that gets oxidized. Okay. All right, so if we're looking at an oxidation reagent or an oxidant, it's the thing that's causing the other thing to be oxidized, right? It's inducing that oxidation reaction. So it has to be the one getting reduced because both things have to happen, right? We have a reduction reagent or a reductant where we have the thing that gets oxidized, right? It's inducing the reduction reaction. Okay. So how does this play into a regular reaction that we might see? The whole thing with redox reactions is that it's all about the electron, right? It's this transfer of electrons from one species to another. So one example that we have is this reaction here, where we have aluminum solid and copper 2 plus going to aluminum 3 plus and copper solid. If we need to balance a redox reaction, we need to know how many electrons are being transferred from the reductant and the oxidant to each other, right? We need to know what that electron transfer is. So how we do that is we identify our oxidation numbers first, right? And an oxidation number is just the state that the species is in, right? You do this specifically for every element that's in the reaction, right? So even if you had something that was H2O, right, this would have two oxidation numbers, one for the H and one for the O. Okay, does that make sense? If we want to do the oxidation numbers for all of these species, what is that aluminum going to be? Why is it 0? Yep, so it is going to be 0. It's a solid because it's in its elemental state. Right, aluminum is a metal, and so since it's in its metal form, it gets a 0. What is the oxidation number of copper 2 plus here? 2 plus, yep. Okay. This is the good thing to know first. If you have a charge on your species, whether that be a singular element or that be a combination of elements, your oxidation numbers need to add up to the charge on that species. So since we have 2 plus on copper, that means we have to have an overall charge of 2 plus or an overall oxidation state of 2 plus. What would our combination of oxidation states have to equal for H2O? It would have to be 0, right? There's no charge on water, so we can have a no oxidation state that's plus or minus, right? The total has to be 0. Does that make sense? Questions? So what does that mean for aluminum 3 plus? What's our oxidation state there? 3 plus. And what about copper solid? 0. Good. Okay, so we can see that we go from, bless you, we go from 0 to 3 plus, and we go from +2 to 0. So what is the 0 to +3? We're getting more positive, so is that oxidation or reduction? This is oxidation. What does that mean about our +2 to 0? That's just the reduction reaction. Okay. How I like to remember this, I like to remember oxidation only. Right, so I say oxidation is the OX. You're going to lose electrons. You're going to get more positive. And I highlight all of my O's. So oxidation is losing electrons and getting more positive. So all of those O's together within your description, you can say, okay, all of those have to go to oxidation. you know oxidation, you know what reduction is because it has to be the opposite. Reduction, you're going to be gaining electrons and you're going to be getting more negative. Okay. So if we want to find out how many electrons are being or any questions on oxidation and what I just talked about. So if we want to know how many electrons are being transferred in our redox reaction, we have to write out our half reactions in order to balance the charge and in order to balance the overall reaction in general. Okay, so you break your half reactions into the oxidation reaction and then the reduction reaction. So we'll start first with the oxidation, and we'll have aluminum solid going to aluminum 3+. If we're being oxidized, do we think that your electrons are going to be a product or a reactant? We're going to be losing electrons. Product, right? If we're losing electrons, we're giving them up. We have them now, and I throw them away, so they're going to end up as a product. How many electrons are we giving up? We're giving up 3, right? Just like we have to have the equal number of aluminums on both sides of the equation, we need to have equal charge on both sides of the equation. Since we have 0 on the left, we need to have 0 on the right. We have +3 from our aluminum 3+, so we need to negate that by having 3 electrons to cancel those out. Does that make sense how we're doing both of those? Okay. So the other thing you can write down in your oxidation of things that, like a characteristic of an oxidation reaction, is one more of saying that electrons are products. Right? And you have that O again in products. The next thing we can write out is our reduction reaction. So we have copper 2+ going to copper solid. Which side are our electrons going to be on this side? Yep, they'll be on the reactant side. And how many do we have? We have 2. So if we added the 2 half reactions together, if you kind of think about like Hess's law, right, where you can add all of your reactions to get to the final, would we end up with the original equation that we had? Exactly how we had it? Why? What do we have instead? Right, we have, it's not balanced. Why isn't it balanced? Good, right? So aluminum has 3 electrons. Copper has 2 electrons. So if we added those together, it would like saying we would have just a single X on one side, right? We don't want to have any electrons in our reaction. So we need to balance this charge so that an equal number of electrons are being shared from the redox reaction and from the oxidation reaction. So how are we going to balance 3 and 2? What do we need to do? We need to put coefficients. So what coefficients are we going to put in front of the aluminum? Yep, we're going to multiply this whole reaction by 2. So we end up with 2 aluminum solid, 2 aluminum 2+, and 6 electrons. And what do we multiply our copper equation by? Multiply this by 3. So we end up with 6 electrons, 3 copper, 2+, and 3 copper solid. Now, if we added those together, we would end up with 2 aluminum plus 3 copper 2+ goes to 2 aluminum Are all of our elements balanced in terms of aluminum and copper? Yep. How about our charges? Is our charge equal on both sides? Why, yes. Mhm. Good, right? We have 3, 2 plus from the copper, so that's a total of 6 positive charges. And we have, oh, sorry, I wrote the wrong number. And then we have 2 3 plus charges from the aluminum, which is again a total of 6 positive charges. So our elements are equal and our charges are equal. So if I were to ask you how many electrons were transferred, what is the answer? 6 electrons. One's balanced, it's positive charges. Yep. Go ahead.
Is that the N value?
Yes. Yep. So this is N. Yes. So you would have to go back to your half reactions. So you balance your charges within your half reactions. Because then that's where you see, like, the whole point of the redox reaction is that these electrons are never actually in solution, right? You can't like zoom in and be like, oh, there's the electron that's being transferred. That doesn't happen. But the half reactions break it down so that you can see, okay, this one's giving up 3 electrons, this one's giving up 2 electrons. So overall, what's actually happening that way. Sometimes you'll get lucky and it'll just be like 2 electrons are being transferred and you know that it's 2 right away from the half reaction. You don't need to do any extra balancing. But if they're not equal, then you just have to go back to your half reactions and see if you can multiply them by different coefficients. Yes. Yep. Yes. Yep. You want to make sure that everything that's going into the reaction from an electron is being produced as a product for the electrons as well. Any questions on this? Do you want to try another example? Okay, so this will just be, we'll do a couple where you just have to balance the half reaction, and then we'll do a couple where you have to balance the full reaction. Actually, for this one, just balance. Okay, you want to try these on your own or walk them together? Let's walk through the first one. Okay, let's walk through. We'll do one from the left and then give you time to work on those, and then we'll do the other two. Okay, so I just want you to balance the half reactions, right? So this came from an overall reaction like we just talked about, but this time we're writing out either the reduction or the oxidation reaction. Okay, so for balancing the reaction, what's the first thing we need to do? Yep. Good. Yep. So what would we do there? Awesome, right? So that 2 off the Cl2 is saying that we have 2 chlorine atoms, but there's only 1 on the right. So we need to put a 2 in here, and now our chlorines are now balanced. What's the next thing we look at? Okay, so now we need to look at charge. How much charge do we have on the left-hand side in our reactants? 0. How about the right-hand side in our products? We have -2, right? Yep. So where are we going to put our electrons in order to balance our charges? We're going to put them on the left side, right? We just looked at stuff that was positive, but this time we're looking at stuff that's negative. So our overall reaction would be Cl2 plus 2E minus is going to 2Cl minus. Right, we're not making things add up to 0 now, we're making things add up to -2. Does that make sense for this one? Okay, it says reduction or oxidation. Why? Yes, right, so our electrons are in our reactants, so we're gaining electrons. If you're to look at oxidation states, chlorine 2 is second. What oxidation state does that have? That's 0. What about Cl minus? That's -1. But we have 2 of those. We have overall a -2. And so we go from 0 to -1. That's getting more negative. And so that means we're reducing. So this is a reduction reaction. Does that make sense how we did this one? Can we try 2 and 3? Yeah, I'll give you a couple minutes. Mm-hmm. That's a good question. Cl2 minus. I think it would be -1. Yes, yep. Yes. Yep. Actually, even when it has the subscript, it's still multiplied. So like in the NO2 on the right, do you know what oxidation state oxygen always has? So this would be -2. So it overall has you have two of those that are both at -2. So then it's -4 plus 4. Yeah. Yes. Overall, like I would have a -1, but it overall be -3. Yeah. I'm sorry, I lied to you again. I'm switching back and forth between a couple of things. Sorry. So with the I3, right, the big portion here is that this whole thing, I3 needs to have an overall -1 charge. This has a weird Lewis structure, right? So each of the I's in that structure will have a different oxidation state because it has resonance and whatever. Overall, it'll be -1 because the charge is -1. Overall, the NO2 has to be 0, but because NO2 is symmetrical, or almost symmetrical, it has a clear-cut oxidation state for the oxygens. Your I's would be a little weird in terms of its oxidation state, but overall, that whole thing has to equal -1 because the charge on it is -1. Yes. Yep. Right. So if we had, I don't know, whatever, I3 -1, overall, that has to equal -1. So yes. So right, in this case, when it's bonded, the I's would all have a -1 charge because it's a halogen, right? So then that would have an overall -3. But to have a -2 overall as your charge, this needs to be a +2. Right. So when it's by itself, it's funky, but when it's like in the compound, then it's overall going to be minus. I think for the halogens, that's how it works. Right. And I- in that one is just going to be -1. Right. So then you just have -1 here. Okay. Does that help a little bit to make it a little confusing? But I think the more you practice with it, the more you'll see it too. Okay. Did we get an answer for 2? What our half reaction looks like? What does it look like? Sorry, for 2, for the iron. Okay, so we can't do that one because how many irons do we have on our left? How many irons do we have on our right? Also 1. So what happens if we do coefficients? So instead of balancing with coefficients, what do we balance with instead? Electrons. So what is where do we need to put an electron to make our charges equal? like that. Okay. And what kind of reaction is this one? This is oxidation. Okay. And then what about our I3 minus one? What do we think we have to do for this one? How many I's do we have on our left? 3. How many I's do we have on our right? 1. So what do we need to do first? And how do we change that? Okay, how is our charges doing? Say it again. It's product heavy, so how do we fix that? Okay, and so is this reduction or oxidation? This is reduction. What is our N for question 1? 2. What is our N for question 2? 1. What is our N for question 3? 2. Questions on that? Yes. Yep. So right in this one up here that we did where we had the full reaction, overall your ends need to match. So you need to have both of them. Here we're just looking at half reactions, so it doesn't matter. We could write the ends for the half reaction and say, okay, in our aluminum, N was equal to 3. In our copper, N was equal to 2. And since those don't match, that's why we need to balance them for charge. Does that make sense? Alrighty. So for 1 and 2 on this side, right? We just want to write out the half reactions. We're not going to balance them just yet. So we kind of started talking, we'll do 1 together and then you can try 2 on your own. But we kind of started talking about NO2. We said that oxygen will always have an oxidation state of -2. And then since this NO2 has no charge, that means our N has to be +4. What's happening here though? How many? We go from 1 reactant to 2 products. So what does that mean? What do we think is going to happen? Coefficients might change. What about in terms of oxidation states? Do we know what's getting oxidized? Do we know what's getting reduced? Can we figure that out if we don't know? Yeah, we can. Okay, so let's prove it. What's our oxidation state on oxygen in NO3 minus? Overall -6 because this is -2. So overall -4. Sorry, not -4, -6. So what does that mean for nitrogen in that NO3 minus? Has to be +5, right? We need to say, okay, we have 6 negative charges. We need to have an overall of -1. So +5 will get us there. What about just the NO? What's our oxidation state on oxygen? -2. What about nitrogen here? +2. So nitrogen went to +5 and it also went to +2. So what did nitrogen do? It did both, actually, right? If we go from here to here, what are we doing? We're losing electrons. So you get oxidized here. But if we go from here to here, what do we do? We gained some electrons, and so we got reduced. Okay, so if we write out the half reactions, we would have NO2 goes to NO3 minus, and NO2 goes to NO. That's all we can do for right now because you have to mess around with the oxygens a little bit if you're going to do anything else. So we can just write that half reaction. Or those two half reactions. Okay, so now give 2 a shot. See if you can write those half reactions. Alrighty, we have half reactions. Okay, what's our oxidation states on all of these first? What about that SN? What is going to be that oxidation state? This is 0. What about nitrogen? +5. Oxygen? -6 because it came from -2. What about SN on the product side? +4. Oxygen, we said, is still -2, so overall -4. What about nitrogen? Also +4. Same thing, -2. For like SN and O2? Yes, yep. Yes, so you first want to look at your overall charge and see that it's 0, see that it's neutral. Look at what you know. Oxygen would be that oxidation state. You know that that one's going to be -2. And then because you have -2, you have 2 of those is -4 and it has to equal 0. And then you say, okay, SN has to be +4. Oh. Okay. um Yes. Yep. So then like the overall charge of SNO2 is 0. Yeah. So you have to look at that in order to determine the oxidation state of usually the metal component. Sorry, I mean overall charge for that oxygen. Yeah. Like the total charge from that oxygen would be -4, but the molecules overall. Yeah. Okay. So if we're looking at, so when you break your half reactions up, you're looking at your same elements that need to stay together. So what happens between SN and SNO2? And that is SN goes to SNO2. And what happens as we go from NO3 to NO2? This would be reduction because we have NO3 minus goes to NO2. Because you need to balance your oxygens and other things before you can write the electrons for the ones on the right. So this is just breaking it up for now. When you're done, if you want more practice, you can try and balance these equations. Okay, any questions on the left and right hand sides we just did? Feel a little bit more comfortable with like half reactions and oxidation numbers, all that fun stuff. Okay. So, right, I said that you can't solve, or you can't just directly do the oxidate or the electrons here for the ones on the right, because you have to balance them according to sometimes an acidic or a basic solution. Did we get that far in class? Okay. Do you want to do a practice of that one? Let me pull up my example. Sure. Okay. So we're going to balance in an acidic solution. And we'll have this is what I want. Maybe hold on. Sorry, we're going to do 2 half reactions side by side. Okay, so we have MnO4 minus goes to Mn2 plus, and then we have Cr3 plus goes to Cr2O7 2 minus. Okay. Did anyone look at his notes and how he goes through it and how to solve it in the steps? Okay. I think there's many ways. It doesn't have to be in this exact order, but that's a definitely fine way to do it. So we can just follow his way. If you like going a different way, feel free to just tune me out and do your own thing. But I think this is fine the way he does it. Okay, so the first thing you have to do, right, is you wrote your half reaction. We're first going to balance our he balances the electrons first. I like to balance the species that are not O and H first. So in MnO4 minus goes to Mn2 plus. I like to make sure that everything that's not your oxygens, your hydrogens, or your electrons are balanced first. So in that case, if we have MnO4 minus on the left and Mn2 plus on the right, do we need to do anything to balance this? Nope. So step one, we said balance everything but O, H, and electrons. Yes. Yep. Right. So if we're looking at, I guess I should do this in two different colors. If we're looking at this chromium 3 plus going to Cr2O7 2 minus, right? First thing is to balance everything that's not oxygen, hydrogen, electrons. What do we need to do to balance this one? We're balancing everything but oxygens, hydrogens, and electrons. So we just need to balance that chromium. Yes, right. We would need to put a 2 here so that we have 2 chromiums on our left and 2 chromiums on our right. No. um, yeah, yeah. Just look at it that way. You can balance it by charge if it's just its species, right? This one, the aluminum and copper, right? Those were just single by themselves. So you can look at the charges. When we have other stuff involved, then we have to look at specifically how many of each you have on both sides. Okay. Okay, so then step 2, I like to balance my oxygens. Let me rewrite this in purple so that it looks nice. Okay, so if we're balancing our oxygens, where do we have an excess of oxygens? Yeah. The reactant side. So how do we balance our oxygens? What do we add to the solution? We add water. So how much water do we need to add? We need to add 4 waters, right? We have 4 in our reactant side, and it's H2O, which always has a single amount of water molecules or oxygen water molecules. So we'll have MnO4 minus go to Mn2 plus and 4 H2O. Questions on waters? What do you do to the chromium? 7 waters, right? We'll have 7 H2O plus 2 Cr3 plus goes to Cr2O7 2 minus. Okay, so what new element do we just add to the reaction? We added hydrogen. So now the next thing you're going to do is you're going to balance H plus. How are we going to balance H plus for our manganese reaction? Why 4 hydrogens? 4, 8. Good, right? So even though we added 4 water molecules, there's 2 H's in every water molecule. So you'll have 8 that you need to add to your left-hand side to balance out the hydrogens from the water. And what do we do for our chromium? Yes, right? We added 7. So 7 times 2 is going to be 14. So now everything is balanced except for our hydrogen, or except for our electrons. So step 4 would be balance electrons. Yeah, he does balance electrons first, and then he balances everything other than oxygen and hydrogen, then balances charges again, and then balances oxygens and then he checks by counting the hydrogen atoms. I personally like my way better, but if you like his way better, by all means follow it. I just think this has a better flow to it because you can see like overall charge, and you only check for charge one time. But he also is a professor. I am not, so okay, so now we need to balance our electrons, and we balance the electrons by looking at our charges. How much is our total charge on our reactant side for our manganese? +7, I like. Yep. Right, so we have 7 plus charges from our hydrogen ions, and we have 1 minus charge from our MnO4. So overall, this is going to be -7 for our reactant side. Sorry, +7. How much charge do we have on our product side? +2. So where do we add our electrons to make those equal? The react, how many? 5. Awesome. So we'll have what? So we'll have 5 electrons, 8 hydrogen ions, MnO4 minus, Mn2 plus, and 4 H2O. And then how about our chromium? How much charge is on our reactant side? Go ahead. So we have +7 on the reactants, and we have +2 on the products. So in order to get those equal, right, we can't bring +2 up to +7. We have to bring +7 down to 2. So you need 5 negative charges in order to make that happen. Right, if we subtracted +2 from +7, you end up with +5 is the overall. Yes. Right, because we added protons with the H plus. Yes, yep. So if it was OH, so if it was a basic condition, then between 3 and 4, you balance your H pluses with OH minuses. And then you mostly have negative charges, right? Your reactant side is positive and your product side is positive here. If it's in your basic solution, then you mostly have negative charges. So then you have to bring 1 negative, more negative. Does that make sense? If we do an example, it kind of makes a little more sense. But we don't need to get that complicated yet. Okay, and then for our chromium, what are we doing in order to balance our charge? How much charge do we have on our reactant side? What about our product side? 16. Yep. So how many electrons do we need to add here? We need to add 10. So we'll have, and they're going to the reactants or product side? Products. Yeah.
Where did the +2 come in on the CR2
Yep. So we have 14 H pluses. So we have 14 positive charges there. And then 2 positive charges. Oh, I'm sorry. It was a -2. Sorry, I was getting late, y'all. Okay, so this should be 12. Thank you. Yes, yep. Okay, so how many electrons are we adding this time? 6, yep. And then they go in products or reactants? Products, yep. So you have 7 H2O plus 2 Cr3 plus goes to Cr2 O72 minus plus 14 H plus 6 electrons. Okay, if we wanted to make this an overall reaction, what would have to happen? Yep. So if we wanted to combine both of these to get an overall chemical reaction, we would have to multiply the purple equation by 6 and the blue equation by 5. That's a lot of math. We'll do it just so you get an example. We should have 30 electrons, 8 by 6. What would what? You tell me. Right, so we're saying N is equal to 30 here. And then what would our overall reaction be? How do we solve that? How do we find our overall chemical reaction? Yep, so we're going to take this guy here and this guy here, right? We'll line them up so that our arrows are on, right? It's kind of considered an equal sign. So what happens to our electrons? They're going to cancel. What happens to our H2Os? Yep, what side was going to have water at the end?
Yeah.
Yep, we're going to, all your 24 will be used up and we'll end up with 11 H2O. What about our hydrogens? It'll only be on the products. Yep, all of our 42 will get used up and we'll end up with 28 hydrogens on the products. Does anything else cancel out? Nope, so those are gonna stay in the compound, so those won't move. So nothing else cancels out, so we just end up with 6 MnO4 minus, 10 Cr3 plus, 6 Mn2 plus, and 5 Cr2, O72 minus, plus 28H plus. He might ask you to just solve for one of them in an acidic solution, so just solve one half reaction in acidic solution, and then you would stop here. Yeah, you would stop here for balancing a half reaction in an acidic solution. Yeah. Yep. Yes. Yep. If you wanted to balance this in a basic solution, you could solve it here in an acidic solution. So there's two ways you can solve it in a basic solution. Thank you. In between step 3 and 4, you could use oxygen or hydroxide ions in order to cancel out any hydrogen ions you have. So when you have, right, H plus on this side, you would, right, and you have something else, plus A goes to B plus some water. Is what it would look like here. You would add OH minus to both sides. H plus and OH minus create H2O. And so you're left with hydroxide. You now formed a water on your left-hand side, and you have 2 waters on your right-hand side. So this will cancel out with one of these. And you're left with A goes to B plus H2O and OH minus. Yeah, you'll add equal number of oxygen of hydroxide to both sides. The other way you can do, right, and that would be in between step 3 and 4 above. The other thing you could do is you can get to this red equation here and then do the same thing where you have plus 28 OH minus plus 28 OH minus. You end up with, right, this is going to form 28 water molecules, which will then be more than the 11 you have. So that it'll end up with 28 OH minus 6 MnO4 minus 10 chromium 3 plus 6 manganese 2 plus 5 Cr2 7 minus 17 H2Os. Say that again. Yes, yep, we already balanced the electrons, and so that's why you add it to both sides, because you're adding the same amount of positive and negative charge both sides, or you're adding the same number of negative charges to both sides. And the other way, when you're putting it between 3 and 4, now you're left with a negative charge in the OH minus on your products, so then you would add an electron on your reactants. This would be E minus A, B, H2O, and OH minus. Does that make sense-ish a little bit? There's plenty of practice problems out there. If you just want to look up balancing in a basic solution, it will tell you everything. And again, I solved it balancing different ways than Dr. Lindahl does it in the slides. So pick your favorite. If you like a different way, by all means, go ahead. Just something that feels right in your head. Are there any other questions? Do we feel a little bit more comfortable with redox reactions of an acidic solution? Okay, what is it? Bless you. Bless you. Mm-hmm. CR 3+. Okay. So what's 1/2 reaction? Mm-hmm. So you said CR 3+, right? Or just CR 3? Okay, and then what's our other half reaction? Okay, so let's go through it. What do you do first? You don't really have to do oxidation states right now. So do you want to balance everything but? So what do you do to the chromium reaction? Yep. So you'll have CR2, O7, 2 minus, goes to 2, CR3+. And what about the H2O2 goes to O2? Nothing, right? So that's just going to stay H2O2. Goes to O2. Hey, what do we balance after we've balanced everything but hydrogen and oxygens? Yep, you could do it that way. You could balance the oxygens, whatever really you want. Okay. So are you comfortable with balancing that? How would you balance the oxygens? Yep, so you have chromium 2, O7, 2 minus, goes to 2, chromium 3+, and 7 H2O. How many oxygens do we need for H2O2? No. Did I say that this was an acidic solution? It should be. Yeah, okay. Okay, so then once we balance our oxygens, we need to balance our hydrogens. And how do we do that? And how many do we add for the blue equation? And what do we need for the hydrogen peroxide? And what side? Okay, what do we do now? What's our overall reactant charge for the chromium? What about the products? 6. Yep. What about hydrogen peroxide? How much on the reactant side? 0. How much on the product side? For just for the products. It'll still be +2 because we have 2 hydrogen. Yes. Yep. Yes. Okay, so what side is the electrons going on for? Well, how many electrons do we need to add to balance our charge? What side? We'll have 6 electrons, 14 hydrogens. Cr2O72 minus, 2 Cr3 plus, and 7 H2O. And what about 4 hydrogen peroxide? What do we need to do now? Can we add them together yet? Yes. Yep. So since this is 6 and this is 2, we can just multiply the purple by 3. Yep. Better for right now. I tend to do one than the other, but I'll probably, if I were to do this like in an exam or something, I would probably do one on the left-hand side, one on the right-hand side so that I follow it directly. And then I can kind of follow it. Yeah. Okay, and now what can we do? Add and see what sticks, right? What's our N? Just something to identify, I think, really. It might come into play with a couple other equations if I'm thinking you can use that the way I'm thinking you can. But right now it's just something you need to identify. Well, you could just say that like in this reaction, like this many whatever, blah, 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 how many moles of electrons produces this much energy, blah, 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 blah. So then it's like, okay, you have to multiply whatever electron energy you have by 6, and that's how many overall energies you have. Yeah, so there's not a lot in terms of like balancing the equation. It's just like energy stuff afterwards, I think. But in terms of like all this half reaction stuff, this is it. Except if you want to put it in a basic equation. Yeah. Yes. Right. So the only reason you would need to do the oxidation state is if you're like, I have no idea what stuff goes together, right? You're like, I don't know how to write a half reaction. I don't know what goes together in my half reaction. So then you could look at your oxidation states and say, okay, for chromium, right, oxygen is going to be -2. Oops. So overall for that oxygen, it's -14. So chromium has to be what oxidation state? So we have, and then we have an overall charge on the molecule of -2. Yeah, it should be +12, so then divided by 2 would be 6, yes. Okay, so that's +6. We said that oxygen here is going to be -1, which makes sense, right? Because we have 2 of them. And that's going to be an overall of -2, and then H2 would be a +1 overall +2. So this would be +1. Oxygen is going to be 0, and then chromium is going to be +3. So looking at +6 to +3, what do we do? And in our electrons, where do they end up? On the left side, right? So that checks out. And then for our oxygen, what do we do here? We oxidized. And what did we see for our electrons? They're on the right side. Yep. So it's just the only reason you would need your oxidation states is if you're like, what happened, right? If you didn't know, you can't say, okay, chromium and chromium go together, or I don't know where this O2 comes into place because maybe it goes with the chromium or whatever. Then you would have to write your oxidation states. Yep. Zero and +2. Yes. Yep, because H2O2, does that have a charge? No. So that's no charge on the left-hand side, and then how much, and then does oxygen by itself have a charge? Does hydrogen have a charge? Yes. So then that +2 there is the overall product's charge is +2. Yep. Yep. So we said, right, in order to balance these two guys, we need to bring +2 down to 0. So we'll add 2 electrons. And here, in order to bring +12 down to +6, we need to add 6 electrons. I basically do the math of +12, right, sorry, 12 plus -x, right, is equal to +6. And figure that out that way. Any other questions? Do you feel more comfortable? Yeah? Okay. Okay, well, if that's it, I think, is that as far as, I think it's as far as you've covered in class. Electrochemical cells, yeah. He did get past the first side. Yeah, we'll touch on that later then. Alrighty, well, I will let you go then. Thanks for spending some time with me tonight. I'll see y'all in 2 weeks.